Hello. Okay, so today I'm going to do for a change Leetcode Biweekly contest 155, and yeah, so I think some people asked me to do Leetcode contest as well because like they are also helpful for getting better at I guess DSA. Um, like my go-to website was Code Forces when I used to be very active in competitive programming. But yeah, Leetcode contests are also good. So at least for beginners, and like if you're a beginner or maybe somewhere intermediate, so this can be very nice contest for you. I don't know how this interface actually works. uh, this is the contest screen. Okay, multiple problems like this. I think we have to solve them one by one. Okay, let's start from here. So oh, okay, I think there's this dynamic layout feature. Yeah, this looks better. Let's convert to that only. Okay, now so you are given 2D string array. Okay, responses, survey response from ith day, most common response after removing duplicates. Okay, right, if there is a try, return the lexicographically smallest response. Okay, right, right. So I think first we store the frequency like this. For that, right, so we iterate on all the responses. uh, then within each response I want a set of the strings because I want to drop the duplicates. So for I don't know, I guess in the response, like for this day, I want to insert this, right? So this will automatically drop the duplicates, and then everything in this set I will put it into the map and increase the frequency. So for string x in the set s, I will just do frequency of x plus plus, right? So now I have all the frequencies, and I just want the west string. Int max frequency is just 0, and the string answer is also any random value. So now I can iterate on all the elements of this frequency. Okay, I could also convert it into a list of uh, most common response. So yeah, anyway, I could convert it into a list and then do something with it. But yeah, so I can write the frequency is k dot second, and then the string is just k dot first, right? So if the frequency is greater than the max frequency till now, then our answer becomes the string s, and our max frequency becomes this f, right? So we just return the answer, I guess, at the end. Yeah, right. Okay, I think not available during contest. For this case, I think the response should be good, which is correct. And for the second one, it should be bad. Okay. Yes, I think it's correct. We can just try in submitting. Try to submit. Yeah, accepted. So I think that was pretty self-explanatory. Now we move on to the second one. This is unit conversion 1. So I think there's going to be a unit conversion 2 also. Probably not in this contest. So maybe in some future contest, but anyway. So n types of units indexed from 0 to n minus 1 2D array of convergence. Okay. Conversion is like source unit, target unit, conversion factor. I think we multiply something. Okay. Return an array base conversion, base unit conversion of length n. Okay. Convergence is like 0, 1, you can convert it to 2. Okay. Wow, this is medium, yeah. So already it's like a tree problem. I don't know, tree, or it's like a graph problem. So you have weighted edges, and can this ever be like, you know, um, like this could, it might be possible to not. Okay, we have a 2D array. Okay. Then it's easy, I guess. At least it's all connected. Uh, I'm thinking, is this consistent, or do we have to? It is guaranteed that unique 0 can be converted to any other unit through a unique combination of conversions. Yeah. Okay. So since it's a unique combination, that's why, yeah, you can easily do it. Just I think it's just DFS or something on this. Okay, so that's why this will work. You just have to multiply all the convergent factors till now, and without using any conversion in the opposite direction. So that's why this is just a DFS, I guess, on the convergence, or BFS, or any type of traversal simply. Okay. Convergence. Okay. Right. So we just have to write a DFS here. Let's start with 10 to power 9 plus 7. This will be used for the modulo. And I think this is the adjacency list itself. No, it's not. Okay, so we need an adjacency list along with the weights. So we have vector pair intent v, and yeah. Now this is not too easy. Like, this is not as easy as I thought. I didn't think I'll have to, cover concepts like graphs and modular arithmetic this early in the contest. But yeah, anyway, so we just iterate on the convergence. Right? Or actually, we can go like, first we have n equals convergence dot size. Then we can just iterate on this. We right. Okay, just iterate on this, and we add edges. Vi dot pushback. Oh, sorry. Every conversion is a 3 thing. Okay. Okay, 3 things. Right. Temp0, temp1, and then the weight is temp2. right? We just do vx dot pushback w, which is the weight. Sorry, this is y comma w. Okay. So now you have the graph, and then it's just the DFS. We have to do v dot resize n, and we can also have some answer kind of vector int of answer. Then we can also do answer dot resize n, and just we'll do a DFS from 0. We have void DFS. Which vertex we start from and what's the current weight. So we iterate on the adjacency list of this vertex, and then since there's a unique path, so there can be no cycles, I guess, and we don't have to use conversions in opposite direction. We can just do something like DFS. We go to x, and the weight of this edge, sorry, we go to x dot first, and the weight is this current weight plus x dot second, right? Since there are unique paths, you can just do we don't have to do like a Dijkstra, you can just do DFS. Okay, we don't even have to mark visited because there's only one unique path. So then answer of z will just be w, and I think that's it. We just have to return answer, I think. Let's see if it works. Oh, okay, this is actually vector of parent int. Yeah, that's why it's the adjacency list. What? What is this? I did. Oh, sorry. We don't know n. N is actually the maximum element in this convergence. I'm sorry. Okay, and n is actually this size plus 1. Okay, because we are given n minus 1 in these things. So this should be till n minus 1. No. Okay, this doesn't look right. Oh, we don't add this. We'll multiply. And this starts with 1. Yeah, first is 126 and the second one is, I guess, something. Yeah, works. This is adder than I. Oh wow, runtime error. Digit overflow. Okay. Oh, right. Yeah. I forgot modular arithmetic. Ah, this is because of Leetcode. But yeah, so it's actually simple. You just have to do this model. And multiply 1 LL. To convert it to long. This multiplication can overflow, so we can convert it to long and then take modulo m. Right, I'm taking it too lightly, I guess. This one should be even harder. But yeah. M cross n matrix. Horizontal substring is a contiguous sequence of characters read from left to right. Okay. Okay. Right. a vertical substring is from top to bottom. If bottom is reached, then we warp to the next, wrap to the next, and not from the last to the back. You're given a pattern and a grid. You want to find every substring where you find the pattern in the grid. Okay. Right, so this is like a pattern finding kind of thing. For that, we'll use KMP, and I guess that's it. So you'll have to flatten the grid into a string, into a single string actually, and then you will have to yeah. So then you'll have to sort of from that flattened result, you need to get this back, and then it will work, because otherwise pattern finding itself will be very costly. You must use KMP for this. So we can, I think, copy this KMP code, and we'll just use it as it is. Oh, it is Ncube. They have the efficient one also. Yeah. Okay. Let's just use this as it is. So this is an algorithm called KMP, and you can sort of use this to find a substring anywhere inside the string, right? Search for substring in a string. This is the Nuth-Morris-Pratt algorithm, and the idea is to put a hash somewhere in, like you have a pattern, then put a hash, then put the string again, and when you find the prefix function, like you can read about this, it will sort of give you the positions where your pattern is present in the string. So that's what we need to do, and for that we'll have to flatten the array and do some stuff there, right? So let's do that. So we have string, let's call it horizontal, and for that I have, the grid is m cross n. Okay, so m is just m is grid dot size, and then n is grid 0 dot size. Let me call it n cross m, because it's easier for me to use I with n and j with m. Yeah. So this is an empty string. I go from I equal to 0 till I smaller than n, also j. Okay. Inside this, I do horizontal plus equals grid ij. Right, so I have the full string now. Okay, and I have the pattern. So let's call it a string temp is pattern plus we put a hashtag somewhere, and then plus we do the original string, which we called or. Now we get the prefix function of this, which is nothing but prefix function of temp. Okay, so we can use this to get whether a certain cell belongs to this one. Let's call it pf or. This is the prefix function of horizontal, and then we also need the vertical string. Or do we need the vertical string? Can't we just we can actually reflect that matrix we can take the transpose of this, and then that will be the horizontal string again. So we can have a vector of Boolean, I guess, which is like answer. Let's make it of the same size, n comma n, n comma m. Okay, so all of them are initially false, and like this has to be true for some of these. So I already have the prefix function. Let's now try to write this loop again and get this thing done. Okay, so now we want to update answer ij here. So we can do this is or equal to some condition that we'll put here. So what should that be? This means we need the location of that character. Okay, the location is nothing but m times I plus j, right? So this is the location of this, and I want to check whether this is present in any pattern or not. So the way we do it is by checking if like we'll have to check at this spot whether this satisfies the uh, prefix function or not, and then all of these have to be true. So how will that work? We can also store the positions where we have found this vector int positions. We can do something like this, and we can find all the positions where we found the pattern. Okay, so now let's just say that we want to check if temp of I, the prefix function for this, like we want to check if it is equal to the pattern size. So in this we have added the size of the pattern. Let's call it ps, which is pattern dot size, and there's also a hash there. So basically let's call it required. It is I plus pattern size plus 1. Right now here, if the value is pattern size, then that means this is the correct position. So if the pf horizontal of required is equal to the pattern size itself, then that means we've like if we've used KMP correctly, so then that means that we have found the pattern here. So we can just say positions dot pushback. We can do I here, right? So we know the endpoints of all the indices where this is present, right? So now what we can do is we can try to find this location inside positions. So we can do auto it equal to lower bound in positions dot begin positions dot end of the location, right? So we found the lower bound of this location in this iterator, right? Now if it is not equal to positions dot end, that means we were able to find it, and if we dereference it, the just greater one is the like definitely greater, and if we subtract the pattern size from it, I can actually take this out. Right, so if we subtract the pattern size from this and add 1, so like if we subtract 5 from this and add 1, if this value is sort of um, smaller equal to the location, then that means this location lies inside this pattern, because like from this point you find the next ending point, and you subtract the pattern size and add 1. This has to be smaller equal to the location it is present. So this means you can do something like this: answer equals 1. That means we have found the pattern here. So this I have done it for the horizontal, right? Now we have to do it for vertical as well. So to do that, what I can do is I can simply transpose this whole thing once, and then I think we're done, right? Let's say this whole thing is happening in a loop or in a function, I guess. Mm, Can I just copy paste it and write another thing for this? Probably that will be easier, right? So I can just write string vertical, which is again this thing. Now let's take this, right? Instead of horizontal, this is vertical. And for this one, I think this will become, I think this loop has to go out and this has to come in, right? So essentially first we are iterating on the j and then I, so that I think I messed up horizontal and vertical. No. Yeah, first we iterate on j. So that means we're iterating like this. Doesn't matter, right? No. Yeah, so I is increasing first. So it is going vertically now. Yeah, this is the vertical string. Now again we can do like temp equals pattern plus hashtag plus the vertical string. Now we can do, instead of pf or, this will be pf var, the prefix function in the vertical direction, right? Positions we are already having, so we'll just clear it. Okay, now I think almost the same thing we have to do. This is pf vertical, right? So we have the correct positions now. Now we have to do something like this. The only difference now is that the location is different. So this time it is n into j. Yeah, n into j plus I. Right? I think everything else should stay the same, right? And then we have the answer for everywhere. And what do we have to do? What do we output? We output the count. Is it either or? No. Okay, it's an and thing. Right. It's an and thing. So we can start off with true everywhere, right? And if this works, then it's fine. But if it doesn't work, in if we don't do anything, and in else we do it, we set 0 here, a false here. So if is empty, and in else we make it false, right? Now what do we have to do? We just have to print the count. So for that we can iterate on this and the count. Let's just simply iterate this. Count plus equals, let's just say answer ij. Right, so we have to start off with int count 0 and we just return the count. Oh, this is tougher than I expected. I mean, at least lengthier than I expected. IT is declared twice, I guess. What? ITR. Oh, sorry, IT. Okay. For the first case, it is 1. For the second case, it is 4. For the third case, it is 1 again. I think it's working. Oh, wow. Yeah, but we had to use prefix function. Uh, I think I'll cover it in some time. Let's move to the next problem first. I'll do a quick walkthrough of the solutions at the end. Yeah, let's do the next thing. Maximum profit from valid topological order in DAG. I thought these problems would be like very easy for beginners or something like that, but I think they're not that easy. They're more standard, like you can quickly, like if you know these concepts, you can just very quickly figure these out, but they're not too simple. Yeah. So you have a directed acyclic graph represented by 2D edges. Okay, edges, and then score at each node. It's a tree, I guess. You must process the nodes in a valid topological order. Each node is assigned a one based position in the processing order. Okay. Profit is calculated by summing the product of each node score and its position in the ordering. Score and the position in the ordering. Return the maximum possible profit achievable with an optimal topological order. Okay. Wow. Uh, they probably want us to do a greedy sort of thing. Like there are multiple first nodes possible, so you just pick any one of them. But then, not sure if greedy works there. If two nodes could be picked at the same time, which one would you want to pick first? That's the question. You can pick the worst node first, and then you get a very good node next. Okay. Wow. So then, okay, n is very small. Yeah. So as I suspected, this does not have a polynomial time solution. That's why n is very small, and you have to sort of do an exponential solution here, right? So you'll have to try basically every permutation, which is a valid topological ordering. So you have to try all of them out, and for that you use a bit mask type of thing for that, right? I really don't want to do this. So this is an exponential solution. We will have a bit mask of which we have visited and what is the uh, like which of the ones are like still alive, and then also what's the current position. I think that can be calculated from the bit mask itself, right? So in the bit mask we kind of have to check which other bit masks can lead to this. Okay, and we need the maximum score of that, right? So something like that we need to do. We also need the context of at which current node I am right now. Or can we start it from anywhere? Yeah, we can start it from anywhere actually. Okay. But yeah, in each iteration, we'll have to kind of see if like how many incoming edges are like still present for this. Okay. So this is the bitmask DP. I really don't like this. we have a dp and then dp dot resize 2 to power n. Okay, now void solve int mask, right? So we have a bit mask here, and so the answer is just dp of mask if answer is not -1, just return the answer itself. Otherwise, you calculate the answer and return it. To calculate the answer, you will need the edges and also the score. Okay, so we can, I think, keep that somewhere here. We can do s equals score, where the score is outside, int n, let's call it n. We don't need n, we can just count the bits in this, like work with that. So s is the score. We need the edges, I guess. I think every edge we can represent it as a bit mask itself, right? Right, so I want to represent every edge as a bit mask. Let's iterate on the edges. Right, this is just x to y. Right. Okay, now what else? We kind of want to, I think we can do e dot resize n. So here we quickly want to get for each node whether we can do this one or not. So let's say for int I equals 0, I is smaller than capital N I plus plus. So we'll have to do capital N equals small n. Okay. Now we first see if this is alive in the mask. Right, then only we'll do anything here. So for this we want to check if there's an edge from any of these to the mask, like, or more appropriately, is there an edge from any of the vertices present in the mask for this? So it's like EI and mask. Basically, this should represent bool internal vertex. So this is an internal vertex if you have an edge from any of these to the EI, right? So we want to cover all the from edges, or are these? No, these are not directed from you to any. Yeah. So basically, this is just E of y or equals 2 to power x, right? So that we turn on the xth bit in EY. So in EY, in EI, if the xth bit is on, and in the mask also, if the xth bit is on, that means there's an edge which starts from a vertex which is still alive in the mask and ends at this EI, ends at I. So then that means this is an internal vertex, right? I think we're done with this. Okay, so if it is not an internal vertex, so what we can do is we can actually remove this one. we can do mask XOR equal XOR, let's just say I to the power I. This will be the new mask. We can remove this, and then what will be the position? Okay, I think the position we can find from the mask itself. The position is capital N minus built-in pop count of mask, right? So this is the position. Right, no, +1 I think, because first time you will have first time you have all of these, right? All of these are high, and that's why I will do +1. And when nothing is on, you do n minus 0 plus 1, which is n plus 1, which is wrong. Okay, I think if mask is 0, then you return 0. If mask equals 0, then you've done everything and you just return 0. Right, so now this value is from 1 to n. So n minus 1 plus 1, it can go like 1 to n, which is fine. So this will be the next mask. So let's just say this is solve of mask this, and we have to multiply with this with the position. No, we add this, summing up product of each node, score, and its position. So we add this, and we add this with the position and the score. 4 of I, right? So this is one candidate from the answer. Like, this is one candidate for the answer. So our answer is min of or max of this temp comma answer. Answer starts with -1, so I think it works. Answer is the max of. Since the graph is a DAG, then there will always be at least one vertex where this is true. So we get the answer, return the answer, and we have memorized it. So it is DP. Right, so we can simply solve for mask. And is the answer just, so the answer is just solve of 2 to power n minus 1. Is that it? Return 0 where? Solve should have a return value. Oh, this is the end. Output 8. Is that correct? Okay, for first test case it is 8. For the second one I think it's 25. Okay, I think this should be fine. Yeah, okay. So I think I've done all now. How do we check? Yeah, all of these are done. Okay, so now let's do a quick wait a second. Yeah. Okay. I think I was pretty. What the fuck? How can they do it in 2 minutes? This has to be some sort of cheating. Like, you can't do all of this in 2 minutes. Doesn't make sense. But yeah, this is from my college. I don't know. But anyway, so let's just try to go through all the problems once. I'll try to make it quick. Right. So in the first problem, we have responses. We want uniques in the row. So we have just done, we have made a set and we get the uniques in the row, and then we sum up the frequency, and then we just want the max frequency. Okay, I think I had to do one more thing. If the frequency is greater or if frequency is the same and S is smaller than the answer. I think this is what I had to do. But I guess they didn't have a test case which sort of gets it wrong. What's this? Yeah, I think this is the right solution. I mean, anyway, like once you have the map of the frequencies, you just have to find which has the maximum frequency and is the lexicographically minimum string. So that's it. But yeah, in the second problem we had to use okay, now this is a very bad problem because only in the constraints they have given that there's the unique conversion that is possible. Anywhere else they didn't give that, right? So without that, this is probably a very tough problem because you can have multiple ways of going, and then like one of them can be smaller or greater. Then you could go reverse, and like so basically this becomes a Bellman-Ford sort of problem with you when you take the logs and everything. So this is a very complicated problem in general, but since they have given unique convergence, then it's just some sort of implementation. Like you can just do a DFS, think of it as a directed graph, and just do a DFS from 0 and keep on multiplying the weights as you get them along the path, and you have to do this modulo arithmetic, and then you're done. This is the second one. Yeah, third one actually requires KMP. So let's take this. Yeah, so KMP is a sort of algorithm in which, like, let's not get too deep into what KMP does, but you can sort of have a pattern, then add a character which is not present in the pattern or the text, and you can append the text here like this, right? So you once you do this, and then you make the KMP array of this. So you can read about KMP algorithm. But yeah, so once you make the KMP array of this thing, wherever, like if this length is P, if the length of the pattern is P, in this array, wherever a P is present, you can say that this is actually equal to the pattern, and it will set this everywhere. And if this length is M and this is N, so it will do this whole thing in M plus N time. So that's what we have to do. So this we can use to find the patterns everywhere. This along with some you can store the positions, do some binary search, all that stuff. So I just basically copied this KMP function from CP algorithms. You can write your own also. I could write my own, but it would have taken more time and like doesn't make any sense. So yeah, then you just flatten the this grid into a long array like this and make the prefix function of that. Then you know the positions where it is present, you put it in a vector, and then you can quickly find whether this belongs to any of the strings by finding the lower bound. So when you find the lower bound, you know the next position where one of these one of these patterns end, and if the start is also before it and the end is also after this, so then that means like the pattern is present there, otherwise it is not. So I start off with true everywhere and I set false in some places. At the end, I'm left with the intersection of both of these, and then that is the count, and I return the count. This was the third one. Now fourth one actually does not have any greedy solution or anything like that. If you try to pick the minimum every time, that will not work. I'll show you why. So I hope you read this problem, but yeah, anyway. So even if you had something like this, uh, okay, let's just make it simple actually. Let's just say the graph is like this. So the score here is 1, and this is 2, and this is 3, and this is oh sorry. So let's say this is 100, this is 101, and this is 1, and this is also 101. Like let's say these are the scores. So if you try anything greedy, like if you try to pick the smallest one first, the problem will be that your score will be 100 plus 2 times 101, and then wait a minute, do you want maximum or minimum? Right, so yeah, you want maximum. So that counter case is like 1, 2, and the problem is like you'll pick this one first, right? So picking this first could have given you a much better option. So like let's say here also you have 1, and here you have, let's say, a very big value, right? So if you try to pick maximum greedily at every step, so first you will pick 1, then you will pick 2 times something. So like in short, the point is that whenever you actually, I think this is also 1. I want to ensure that this comes last, right? That does greedy work here. Wait a second. I should be able to come up with a counter case pretty easily. So I want this to be picked first, and then this to be picked first. After that, this and this. This is the order I want, and I want to make a counter case such that it picks this first, right? So ideally, maybe we don't want this to be the last, right? Uh, we want something else to be last. Maybe this should be the last, or no. I want this to be picked first. If this is smaller than this. Basically, removing this kind of opens this up. And I want this to be second. So that's what I want. I want this to be the second element. If this can be first, this can be second. But if this is first, then this will have to be third. Right? So let's say these are big numbers. Let's say these are all, this is 10,000, this is also, let's say, 10,000. And this is, let's say, a small number. That's why I want it to be second. I don't want it to be third. But since this is also 10,001, what you will do is you will pick this first. Or sorry, if this is like 9999, yeah, I think now I found the case, right? So since this is 9999, your greedy will pick this first, and then only you'll pick this and this and this, and this will be the last, right? So I don't know, whatever greedy you try, you can sort of make a case where the correct order should be this 1, 2, 3, 4, and then you will also have something where your greedy technique will say like this should be the correct answer. 1, 2, and then like your greedy will say that this is the answer. 1, 2, 3, 4 or something. Right, so greedy doesn't work, and you have to sort of try everything out. So that's why we can use bitmask DP here. So we have a mask. The mask is just bits, like a high bit means that this node is still unvisited, and a low bit means that this is visited. So you can have a mask like this, and in just 2 to power n information, 2 to power n unique combinations, you can keep every vector of visited. or unvisited, whatever. So this way you can try out every possible way of doing it. So from the mask itself, you can also get the position at which we are right now. And I did a kind of trick to quickly get this thing. Otherwise, it will be like my current solution is 22 times 2 to the power n. But if I didn't use this thing, it would have been 22 square times 2 to the power n, which might have been too high. But yeah, so this technique is just that you can do a single AND operation to find whether any internal incoming edge is still alive in this mask to the ith vertex. So that's what we've done, and after that it's a very simple problem. It's a simple bitmask GP problem. If you know bitmask GP, it shouldn't be tough. Yeah, that's it for this video. If you like watching such videos, subscribe to my channel, and thank you for watching.